Hi friends, you found my talk from Orlando Code Camp 2024, how the programming for a light show works. If you missed it or you're just interested in the subject, congratulations, you found something that you will probably never use in real life, but I appreciate the look anyway. So let's get started. You'll find the code for this in the links below for the demo code, etc., and some nonsense about me that you can really watch if you're super curious. So let's go back to 1989. I was watching MTV. I was in high school, and this video comes on with Pink Floyd, Delicate Sound of Thunder Tour. They did a bunch of videos from it, and they looked like this, and it blew my freaking mind. I couldn't believe what I was seeing in terms of the motion and the movement of the lights and everything. Never seen anything like that. Most people really hadn't up until that point. Lighting was fairly static, and it usually involved lots of can lights that didn't move. So this was a really big deal. And a lot of it was because of this fixture or ones like it or variations of it before and after in the starting in the very late 80s and then through much of the early 90s. Verilight made these lights and they were just everywhere. It was a big deal. You had to rent the fixtures, you had to rent the technicians. It was a whole thing. But these things really kind of set the tone for what this was going to be like in the future and what we would see on stages everywhere. And if you watch a lot of music videos, concert videos from that time, you'll see these things. They're easy to pick out because they're so blocky and square. Very easy to find. And apparently this company, QSale, they will sell you one. They don't work the same. They have some kind of electronics they add to them, but they are obviously kind of relics and maybe collector's items? I don't know. Anyway, then a couple of years ago, 2 years ago, I go to Cleveland to see Tears for Fears, and I see this, and this blows my mind even further. A little bit later then, you can see just last Halloween, this is what it looked like in front of my house. Yes, I have a serious fog machine, and it does that. And the neighbors thought the police were there or something, which was kind of fun. Anyway, so how are these things controlled? Let's walk through the actual basics of lighting control in terms of the protocols and whatnot. It starts with something called DMX. It stands for digital multiplex. It's been around for literally decades at this point, and it is a standard that lives on today in all kinds of different equipment. RS-45 is the electrical signal standard that's associated with it. If you really want to get into the voltages and things, you can look that up on the internets. The way that you connect to things is with XLR connectors. 5-pin is the official, with 5 wires, is the official actual standard. But a lot of stuff uses three pins now because 2 of them aren't technically used most of the time. And these 3-pin cables are basically standard microphone cables, and so that's what you're going to see connected to my stuff today. A controller then connects to a fixture, and then that connects to another, etc., etc. They're basically daisy chains, so they're easy to set up in that respect. Here's the setup that we're looking at today. On the right, you have a controller. It's that little silver box. There's a microphone cable you can see going into the first fixture, and then there's one coming out of that goes into the second fixture. So if you can imagine, you can have these things chained on a stage, one after another, or up in a rig, of course. So how does DMX itself work? 512 bytes are sent down the wire. It's really that simple. Each byte has a value between 0 and 255 because, duh, that's what a byte is. I'm not insulting your intelligence, just pointing it out. And then each byte corresponds to a channel. The fixture, or the dimmer, can listen to at least one channel. So what I'm saying in that case is like a dimmer constitutes your basic theatrical light, where somewhere backstage there's a rack full of dimmers, and those dimmers have wires that come out of them to different places around the theater that lights are plugged into, and they dim them from completely off to completely on, or somewhere in between. The moving lights have, obviously more than one channel, and they can listen for all kinds of different things. The first channel is referred to as its starting address. So, for example, if the first channel for a light fixture controls the panning of it, and its starting address is 26, then 26 would be the first panning channel, or the first channel. 27 will be its second, which might be the fine control for pan. The one after that might be tilt, etc. But anyway, they start from that sequence. They refer to that as a patch. You'll hear that terminology used all the time. That comes from a day when you actually had to patch wires between controlling systems and actual dimmers. But the word has continued to persist over the years in terms of the electronic control of these things. We send this blast of bytes out at a frequency of 44 hertz at the most. You can go as low as 10, I think, and it just depends on the software and the hardware that you have. 40 seems to be the max that most of these things seem to operate, as far as I can tell. So I go back to the DMX channels, and here's a list of the first few for the fixtures that I'm using here today. So you can see that channel 1 is the pan, the second one is the fine control, tilt, fine, pan, tilt, speed. The color wheel, so you can see the ranges. 0 to 6 is white, 7 to 13 is red, etc., etc. Gobo wheel rotation, etc. There's a bunch of different things that we're not going to get deep into here. You can see the dimmer there is number 11. That's an important one. I will say that this particular fixture also has two different modes. It has an 8-channel mode and a 14-channel mode. The 8-channel mode uses fewer channels, but it offers less control. Certain things are just not available. So you can see, for example, there is no fine control for pan and tilt in the 8-channel mode. So it just depends on what your use case is. So we have to ask the question then, how many things can you control? A simple dimmer connected to a plain old theatrical light just requires one channel, as I said earlier. Super simple. The complex fixtures, like these, well, these aren't really complex. These are relatively simple, but they do a lot of different things. So they have channels for dimming, color, pan, tilt, gobo, rotation, all the things that you saw in that previous table. 512 channels together are called a universe. So you can have multiple universes. However, with those XLR connectors, those microphone cables, essentially, you can only have one universe on that cable. You can't send more than one. It only understands, there's no concept of divvying those two things up over that wire. There are different ways to do it, though, however, on higher level protocols, which we'll get to in a moment. The modern controllers, they can control many different universes. You'd see some of them even have the connectors right on the back of them. So they might have 6 connectors on them because they can control 6 different universes. Some rigs also have pixels that are that each have 4 channels, red, green, blue, and white. There are sometimes light fixtures themselves, like a bar or a square that has different pixels in it, and each one of those little dots is controllable over 4 channels for those different colors. Obviously, you mix the different colors to get different shades of whatever it is that you're looking for, and then the white is more of a pure white. So if you think about just your basic LEDs, right? LEDs are in everything now, and you can change the color of them to a zillion things, especially in computers now. I'm not sure how that became a thing, but it did. So same thing, same concept applies. And then there's software that it can essentially map, like, say, a video feed to those different pixels. And you can kind of create interesting effects that way. Sometimes you can use 2 channels together to offer finer grained control, and I had the pan and tilt as an example of that. So I can show you a little bit later why you would have that fine grained control, because remember, if you've got 256 degrees of change, right, and you spread that across 540, what is it? I think these lights can spin 540 degrees total. So that would mean that every single one of those steps in the 0 to 255 would constitute 2 degrees, which doesn't look like a lot when you're looking at it, but when you shine it across the room at a wall, 2 degrees is a lot. It'll change the direction quite a bit. So on top of this, there are other protocols to get DMX into these different fixtures. It's kind of like HTTP is a protocol that we use on top of TCP/IP, and most engineers and developers totally get that concept, right? There are several different popular protocols that send DMX universes over TCP/IP, over Ethernet specifically. SACN, ArtNet, and ETCNet2 are some examples of that. This demo is going to use SACN. Interfaces that receive these protocols typically have the XLR connectors that output the DMX. So earlier I showed you the picture of the silver box. with the XLRs on it. That's the thing that's outputting the DMX from the network. Some expensive fixtures have Ethernet interfaces right in them, so you don't even need the DMX box in the middle. Now, you still have to address them, but the difference is that because it's over Ethernet, and as I said earlier, you can send multiple universes over Ethernet using these different protocols. The listening fixture, you can tell it to listen to a specific channel in a specific universe and send all the universes over the same network. From a programming point of view, it's easier to build packets and send them over the network than it is talking to a DMX interface device that would probably connect through USB. So let me explain that. There are things that you can buy that output DMX from USB, but there's no specific protocol or there's no standard for that. You need to understand how the device actually works and how to send the right signals to it. That's different from the networking protocols, right? Like, you know how to send a packet over TCP/IP, and this demo does exactly that. So, like I said, we're going to use the streaming ACN protocol. It is a multicast protocol. You can also do unicast, but multicast is the default. You're sending UDP packets, which means that they are packets that can theoretically go out of order or get lost, and the receiving thing just says, that's cool, I'm going to move on to the next thing. The IP addresses are very specific for it, and you see those on the screen there. They represent universes 1 through 63,999. So those ranges are specifically the listening addresses of the machines that are going to receive those DMX signals. Each universe requires its own packet to be sent. That's probably goes without saying. So if I have a bunch of things on one universe and a bunch of other things on another universe, I need to keep track of those arrays of bytes in both of them and then send them every 40 times per second or whatever as they change. The interface listens on the IP for the corresponding universe. I said that. And then you can send sync packets so multiple interfaces know that it's time to show the values that were sent all at the same time. So let me break down why that's important. Let's say that you have two different interfaces that are receiving the same universe. The timing of them getting the packet may not be exactly the same, but you can broadcast another packet on the broadcast, or I'm sorry, the multicast for the sync packet, which says to all of them, hey, if you got this one's good to show, turn on your lights. So that can adjust for minor bits of latency. I doubt that that's really a huge issue. I don't know for sure because I don't do this professionally, but I would have to think at 40 times per second, it would be pretty rare to see any significant changes between different interfaces and when they receive things. Let's talk about the different controller systems that are available out there. It is kind of a strange situation because you definitely get what you pay for. There are cheap controllers out there that can do some limited things, and that makes sense because, again, these are pretty simple protocols. So it really gets to how you manipulate math to make them do interesting things, and we'll get into that in the bonus round a little bit later. The industry at the pro level is really a duopoly. You have MA Lighting. They tend to lean more, or be more popular, I would say, among the like concerts, rock concerts and clubs and things like that. They are not, or that is their dominant spot, I would say. ETC Lighting, on the other hand, which bought high-end systems, which used to be a third party, now they own all their stuff as well. They tend to lean more towards the theatrical installations and tours and things. So there are differences in the interfaces and the way that they are controlled. I think the thing for MA3 is that their system tends to be easier to perform with in terms of, pulling up different cues and different colors and sequences and things that you want to show in a rock concert that you want to play, to the band's music. The costs are, it's a crazy range, but what's weird about it is that the core software is the same in the entire range. So the costs go from about $700 to at least $80,000, maybe more, depending on what it is that you need in terms of the whole system. For $700 for ETC, you can get a little USB dongle that unlocks the software. and a network interface that will show. Actually, you could use the one that I have, and you can address two different universes with that, and that's it. On the MA side, they have their cheapest way in is a $2,000 interface. You don't need a USB dongle, but you need the DMX interface. It costs about $2,000. If you want something that you can actually touch and control, they have a control surface that's about $7,000, and then that unlocks what they call parameters, 4,000 parameters. Parameters are a little bit like channels, except that, like in the case of like pan and tilt, where you combine two channels, those count as one parameter in terms of the way that their software counts. The Pro solutions also have some offload processing tools. So if you have a ton of universes and a ton of things going on, and you need to be able to essentially compose all of that data to send over different networks, you can buy these additional machines that sit in a rack somewhere. So let's see some real actual commercial software and what that looks like. So we'll start with the EOS family. They call it the EOS Nomad software, but again, the core of it is the same in all of their products. If you were to buy one of their actual consoles that have built-in screens and everything, you would have a series of buttons that look exactly like this, with a couple of faders on them on the left there. And then this also has a 3D visualizer, so you can actually see, or you can set up a stage for yourself and then see how it looks in real life, which is real handy for programmers who maybe have to set something up before they actually get to sit in the venue in front of the actual console. And then here is Grand MA's flagship product, MA3. This is the thing that you kind of miss here, is that the things at the bottom actually correspond to dials on the control surfaces themselves. So again, if you had a real console, you would have a couple of screens, and they would match up with things that are on there. So like if I wanted to turn on some lights, maybe fan them out here, I can do that. It's pretty easy actually to do stuff like that. And again, they have a 3D visualizer as well. So it's another opportunity to program without being in the venue. And by the way, there are third-party products that you can actually plot out an entire stage, hand it over to somebody, and then import that into the software, and it'll just set it all up for you so that the patch is done. You won't even have to do it. All right, let's see some actual code. Let's see how we control DMX with our own software. Now, I'm using C#. You could use literally any language that can output to some kind of network interface. The concepts are the same regardless of the syntax that you're going to see. So we're going to set up a couple of requirements. First, we just want to control any single DMX channel across two fixtures with a slider control on the screen. That's it. Then bonus round, we'll do some fade some lights in and out in an automated way. That'll be fun. All right, let's get to the actual code here. First, we need to build a network interface. We'll be relying on a fork of the library you see here that is apparently abandoned. I did some fixes on it. This will do the heavy lifting in terms of the packet forming and sending. You can look at that code. I have the fork on my GitHub if you want to see it. It's sort of interesting if you're interested in the way bytes go together to form packets. We need to bind a socket to the local interface, and then we will send the universe, which is 512 bytes, and then following that, we will send a sync packet. So let's look at that particular code. This is fairly straightforward. In our constructor, we are going to set some data that it gets sent in the header of the packet, which is not important really, other than to know that it's the part of the implementation of this particular protocol. When we send a universe, we use the factory to create a packet, and we do that with the values, which are just, again, the numerable of bytes, and the universe number, which is 1, in our case, always, as well as the sequence number. And like I said earlier, that's used for the synchronization process. So we package all of that in there, and then we send it using the sending class. The sync universes is the same general idea, in that we pass in certain payloads into the factory methods that create a sync universe packet and the sequence number. This is sent every cycle to let the listening interfaces know that, hey, it's time for you to update to those values that you just got. And then the polling method is just something that happens periodically to say, hey, we're sending stuff out for this universe. If you're listening and you care about that sort of thing, that's where you go. So let's go back to our slides. Next thing we need to do is build a state mechanism. We're going to include a byte array to hold our DMX values, obviously. And if we did support multiple universes, we would have multiple byte arrays. We'll have a method to assign values, and we'll keep in mind that the arrays are indexed, are zero-based indexes. DMX channels are not. They start at 1, they end at 256, or I'm sorry, 512. So let's look at our state manager. Actually, I have comments on this one. Anyway, here's the byte array, DMX values, pretty straightforward. And then fixtures, we'll show you what that means in a little bit and how those are set up. But in any case, fixtures have a bunch of DMX parameters. Those are things that happen to have the specific channel numbers that are associated with it and the current value. So when we set a DMX value, we're going to just find the particular value that we're trying to change. We're going to again take the channel number, subtract 1 because that's what we want, and then that's the value we will set for it. And then we'll also update that object itself just for reference if the software needed to know it. We add fixtures, that's again part of the other collection there, and then we also have a reset method here. What that will do is it will take the default value of any of those parameters in any fixture and set that, obviously, by calling the set DMX value. Super straightforward. So now we need to figure out a polling mechanism, because remember, we need to update these things every 40 times per second. So first of all, we need a polling timer to send the discovery packets. Again, that's the thing that says, hey, listen to us, we're sending packets out. That is not mandatory. Not all interfaces listen for it, but it is part of the protocol. We need a sending timer to send the current state of the DMX byte array, and we need to do it every 25 milliseconds. And then after sending the data packet, we should also send a sync packet to say, hey, the values that you have are ready to go. If you would please display whatever those values mean to your fixture. This is actually where most of the magic happens, honestly. These are the timers that do the work. So we have a start menu, or a start method rather here, and we're creating 2 timers and starting them. First timer is, again, the one that does the polling, the one that says, hey, listen to us, we're sending stuff out. This fires every 5 seconds, and it's a fairly small packet that says, there's stuff on Universe 1. If you're listening, this is where you find it. The second timer is the one that is actually doing the actual sending here. This one is a little bit different. Again, we're sending every 25 milliseconds, which is 40 times per second. And we have auto reset to false. And what that means is that when the elapsed event has run, it will not run again on the normal interval until we have told it to start again. So that's why when you get to the end of this, we define the event handler for elapsed, and then afterwards we start it. But then also we start it from within the method. And the reason we do that is that we don't want it to, if for some reason this takes too long because the computer's bogged down or something like that, we don't want to get into a situation where we're running them concurrently or getting behind. So that's why we do it this particular way. So first try is we send the universe. This is where the magic happens. This is it. We just take all of those bytes, that byte array, and we give it a sequence number. And then we send universe. So you saw earlier in the network bits that was just that library does that by building a set of headers and then the actual bytes and then the ending part, and that's it. That's the whole thing right there. So as far as updating our actual physical fixtures on the wires, it's just one line. I mean, well, there's the try catch and whatnot, but you get the idea. And then after that, we also try, or rather, we have another call to send the sync packets out to say, okay, we're ready to update. And at the end, we change the sequence number. We roll it over when we get to 0 because it is a single byte value, so it only goes from 0 to 255 in that case. That's it. That's really where the rubber meets the road for the most part. We do have to define some fixtures and their parameters, as well as, and their parameters are channels. I'll get that in a minute. We need these for our user interface because remember we're going to be able to change any individual one of these values by itself. Each fixture has multiple parameters, and then each parameter has a channel number and a default value, as well as its current value. Now the pan and tilt channels, if you remember that chart earlier, actually have two channels that they correspond to. So that gives you 16 bits of precision. And as I said, the reason why is because for a fixture like this that rotates 540 degrees, 8 bits would only give you 256 positions, which ends up being about 2 degrees, which doesn't look like a lot when you're looking at the fixture itself, but shine that across the room at a wall, and 2 degrees might move it over a foot. It's a substantial difference, right? So that's why we have that available. So defining the fixtures, we do that in our orchestrator class. The orchestrator class is basically, it's 3 steps. It's to set up these fixtures that we have, start the polling service, and then which is the timers, and then also send the reset values. So first thing is set up fixtures. These are 2 identical blocks here, and each one of these parameters corresponds to the channel in that particular fixture and its function. So my first fixture has a channel start of 29, which means that with 14 channels, it's going to use 29 through 42. Normally, if I'm at home, I would use this, or yeah, because I do this at home. I would start at 0, but I actually have two more of these fixtures. The ones that I brought with me are actually starting at 29. So the first one is channel 1 through 14, and then the second one is 15 through 28. So the ones I have with me today are 29, start at 29, and 43. So those are the 2, and you'll see these in the UI here in a minute, the names. So that's it. I would add that when I say reset fixtures, remember that at that point, theoretically, there could be latency where the first sending of the bytes would not include the change to the default values. Theoretically, that could happen, right? So when I say reset fixtures, all I'm really doing in that method, as you recall, is I'm just setting up, where is it? I'm just setting the DMX value for those. I'm changing an array in the byte, or I'm changing a byte in the array. So in that case, it's not sending it. That has nothing to do with sending it. So what does that leave? Well, we need a UI for it. So I'm using a Blazor server app. This is not something I would do for probably anything else. Blazor server apps are not the most robust things for scaling. But in this case, it keeps state on the server and it's easy to handle in that respect. So it makes sense for this. So we'll change the fixture dropdown and that'll load the parameters for that fixture in the next dropdown. And then we select whichever one of those we want to change. And then we have the slider to change them to whatever we want. So in the background, we still have the byte array that's being sent every 25 milliseconds. But we are not, by manipulating the UI, we're not manipulating the sending of the bytes. Those bytes are going to send every 25 milliseconds no matter what. All we're doing is we're just changing the bytes with our UI, okay? And there's a lot of reasons why that is important, but we can get to that later. Okay, so now you can see the light fixtures on your screen there. They're just pointing down and to the right, or to the left rather, fairly unexciting. But when we run this, they spring to life, and you can see that they're pointing up at this point. So we've got our UI here. Again, we have 2 fixtures in our first drop down, and then the second one has the various parameters that we can change. So starting with this one, we'll just start messing with the pan, and if you see, we move the slider and it turns around just as you kind of would expect. If we go back to look at the actual debug info here, you can see that I have a line here that says exactly what we're changing. We're changing channel 29 by setting it to whatever this value is. So you can see all these numbers changing as I move the slider up and down. Let's move it around and do some more. Let's change the panning to, let's line it up with the wall, which it roughly, let's go right about, I guess it was where it was, pretty close. And then we'll change, well, let's change the light. Let's turn it on. So we'll go to the dimmer and we'll turn it all the way up. And you can see that it is now on. If we move the tilt, we can point it at the wall so we can actually see it a little closer, see it a little better. There we go. So we can see that it's white. Why don't we change this to a less bright color? I have a color wheel here, so let's go for purple. And then if I want to, I can try to focus it a little bit. It might be too close to the wall for that, but yeah, it's too close. Yeah, it's a little bit sharper. We can also change, we can add a gobo. So we've got a bunch of those that we can change. Let's do that one. We can change it so that it rotates and it can go very fast, or we can go very, very slow. And then we can even add the prism in if we want to. The prism changes 1 into 3, so that's kind of fun too. Now, if we go back to the other fixture, we can do the same thing here. We can turn it on, and then we can tilt it. So you can see there we are. So we can control them both from the same byte array. Pretty straightforward, huh? That's all there is to it. Every time we move the slider, all we're doing is we're changing values in the byte array. And when we do that, it's meanwhile sending those things out every 25 milliseconds. So if you can imagine, software that does this in a big, large way, does this to many, many parameters at the same time, or many channels, and sends them out to change them all and make a show. All right, bonus round. Let's stop that. And we're going to go to the other branch, which is the going further branch. Check that out. All right, so what we're going to do this time, as we look at our deck, is we're going to do a fading bounce effect. So what we're doing here is we're adding an effect base that just cycles through a collection of parameters on a timed basis, and then a derived class from that implements a specific thing that fades these in and out. One goes after the next, and then we do that by letting us know that the by way of the timer that the update has cycled, and by that we're recalculating where in the sequence we would be. So let me explain what that means exactly. If our delta, for example, is 1 second and we're halfway through the second, then that means that our fade would be exactly between 0 and 255, and it would calculate that. So while that's happening, we can still mess with everything in the slider and all that. So to show you, let's just look at the actual code. Under effects here, we have the effect base. This is the part that goes through and looks at the delta that you have and figures out actually looks at the time that you have, and then what is the percentage of progress that you've gone through to get to this particular time at this point in time. So given that percentage, we can send that to the calculate new value, which is not defined in this, but it is defined here in the chaser class. And so based on whatever that percentage is, it's going to figure out where do I fit in terms of the high value or low value, and where we set that up was in the orchestrator. And you can see that our low value is 0, high value is 255. The parameters that we're grabbing here are the dimmers for both fixtures, which remember is channel 11. So 0 index, it's -1, fixture 1, fixture 2, you get the idea. And then the total effect time span we want to be 4 seconds long. So we've done all that, and then we take that chaser's update cycle ID method, and we associate it with the update cycled event on the actual state manager. State manager, on the other hand, has this new code that says when you've got that and you fire that, get the invocation list of event handlers that you've got, and then use the parallel functionality to run them all at the same time and update them all at the same time. So theoretically, right, you've got, let's say, different effects classes that are changing things and animating them, making them dance, changing colors, whatever the case might be. You could have a ton of those running at the same time, but you have to update the math for each one of those every 25 milliseconds in order to update that byte array. So let's go back and look at the actual fixtures as they sit right now. I will run this. You'll see they'll spring back into their automatic, or rather their default positions, and you can see them fading one on and one off at a time. Let's actually tilt them down so you can see them. And we'll change the same one on 2. And there you have it. You can see that effect is now running. It's fading in one and fading out the other, and it does those in sequence. Now, you may have noticed I was able to tilt these things while it was going because it's just another input to change the values in those byte arrays. That's truly all it is. Want to change the color of one of these? Yeah, we can do that too. Let's see where it is. And there we go. That one's red now. If we go to set the other one, we can set the color wheel on that one, and let's see if we can find a blue somewhere. Oh, look at that. First, no, that's cyan. We don't want that. Too light. There's blue. Okay. So now we've got one blue, one red. While we're here, hey, if we wanted to, we can, once again, we can add a gobo in there if we'd like. Of course, it comes off as soon as I change it, right? There we go. I've got it. I went all the way up to the shake range. See, there's different functions there. And then when we come back to it, we'll actually we'll have it spin around. That's fun. And we'll even add the prism. So there you have it. So there we can continue to manipulate these things while the effect is running. And again, all we're doing is changing byte values. That's all there is to it. Now, obviously, I could, fire up the dimmer and start messing with that, and it would conflict with that. However, we don't have code to handle that. So that's it. It's just a matter of manipulating a byte array. That's how you program lights. And $80,000 software can do that for you. Or you can mess around with it and try this as well. So obviously you could probably figure out it'd be pretty easy to do something easy like a straight theatrical show where you're just dimming lights on and off and going from a series of cues, right? You could probably code that in a day, just as an experimental thing. So that's all I got. I hope you enjoyed it. If you have any questions, love to hear those in the comments. Thanks for watching.